Hello everybody, and welcome to Theorem 13.1 on page 95 of the workbook. Let's take a minute and read this together. This is going to be our first major theorem of the chapter about integral domains. Okay, and it says the following. Let R be an integral domain, and let A, B, and C be elements in R. And we'd like to prove that if A is not equal to 0 and AB is equal to AC, then B equals C. Notice that that's exactly the cancellation property that we started a discussion with at the very beginning of the chapter. Okay, so we're trying to prove this nice property that says that if you start with AB equals AC, then you can cancel the A provided that the A is not equal to 0. So it's this property that we'd like a ring to have. We're going to prove that every integral domain really does have that property. Okay, so let's see if we can do that. Okay, so we're proving an if-then statement, so let's start with the if part. So we are assuming that A is not equal to 0 and that AB equals AC. Okay, and we're going to try to show that we can cancel the A's and just get B equals C. Okay, so we'll start by doing some algebra here. Okay, so we started with a statement that looked like AB equals AC, so how about if we just subtract the AC from both sides? So AB minus AC equals 0. And then I claim that we can rewrite that as A times B minus C equals 0. Okay, can we really get away with doing that? Okay, because remember, we're in an abstract ring here. Okay, if these were ordinary real numbers, we'd just be factoring out an A. Okay, well, what's the reason that we can do that here? Well, if you think about that, we're really just using the distributive property. Okay, so over here on the left-hand side, if you take the A and distribute it through, you get what we had over here. Okay, so I want to just make a note here that we can get away with that because of the distributive property. Okay, that's part of the definition of any ring. Okay, so let's clear a little clutter away here. Okay, and now, turns out that what we've got in front of us is exactly what we need to get to where we want to go here. Okay, so here is where we first use the fact that R is an integral domain. Okay, since R is an integral domain, R has no zero divisors. Okay, so what does that mean again? Okay, well, the fact that R has no zero divisors means that if we have a statement like this, a product of two numbers that equals 0, it simply can't happen that both A and B minus C are non-zero. Okay, if it did, we would have a zero divisor. Okay, so since we know that A is not equal to 0, that means that B minus C has to be 0. Okay, that's the only way that this can be true, given that our ring has no zero divisors. Okay, so what we can say then since A is not equal to 0, we must have B minus C equals 0. And if B minus C equals 0, then B equals C. We just add C to both sides, and we're done. Okay, so this theorem illustrates, gives us a little insight into why we made this definition in the first place. The cancellation property is a property that we'd like a ring to have, and we've just proven that an integral domain is a ring that has that property. And you might also notice in the proof that we just wrote, it was very important that we had no zero divisors. That was kind of the key, and that was the reason why we defined an integral domain the way that we did.